Hello everyone, welcome back to my channel. So this is the last few days of the year 2022. So I have decided to make the last video of this year as a Christmas gift and a New Year gift to all of you. We are going to talk about the overview of the 1D breakage population balance equation for this particular video. So I apologize because in the past month, as the university is winding up all the semester for the undergraduate students, in fact, I was a little bit caught up with, and I wasn't able to make any video during this period. But now that I have some time, let us just jump straight and let me just bring you through some of the aspects of the introductory aspects of the 1D breakage population balance equation so that you get a better idea of what to expect when you actually look at and treat the population balance equation for 1D pure breakage. Let's jump straight into it. Now remember, in the past recording we brought up this we show this general population balance equation, which is for a continuous and deterministic system. Okay, so this is the general multi-dimensional population balance equation, multi-dimensional with respect to the internal coordinate and also the external or the spatial coordinate. Right? So let's just do a quick recap on this general population balance equation. So the first term here of this general population balance equation tells us how the number density function evolves with time. And then we say that the second term here tells us how the number density evolves with the internal coordinate space. And this is for the case where your particle or the quantity that you're trying to model is actually changing with respect to the internal coordinate with time. For example, if your crystal or your particle can grow or shrink with time, then you would invoke this second term on the left hand side of the population balance equation. And then this third term here tells us how the number density evolve with the physical space. So if your quantity, the quantity that you're trying to model is actually the number density is actually varying with space, the physical space, then you would have this term in your population balance equation. And then lastly, in the right hand side, or at the right hand side, we have this source and the sink term that describes the case where your particle is actively undergoing, say for example, breakage or aggregation. So when we talk about the breakage population balance equation, this H term here, the source or sink term, is the term that we are going to be mostly talking about. Now, of course, when we say things like breakage population balance equation, this is a very rich term to use because there's a lot of things that is even in the breakage population balance equation itself, there is a lot of things to cover. But obviously in this particular video here, we are just sort of going to give a very brief layman type of overview on the breakage population balance equation so that you get the gist of what's happening, right? And in the future, perhaps then we can go a bit deeper and explain various terms in or various details in the breakage population balance equation. But without wasting much time, let's jump straight into it. So when we look at this multi-dimensional or the general population balance equation, and if we want to get the breakage population balance equation in the one-dimensional form, one-dimensional in the sense of 1D in the internal coordinate. That means that you only model, say for example, the size of your particle. Sometimes the size of your particle can be characterized by, say for example, length and width. In this case, you would have a 2D internal coordinate. But let's say if you only characterize, let's say, the radius of a particle, then you have a 1D population balance equation in terms of the internal coordinate. So let's just first say that we have a very simplistic population balance equation whereby we do not have any physical space variation or spatial variation. And then as far as the internal coordinate is concerned, we only have a one-dimensional internal coordinate, which means that you characterize your particle by a single quantity. Right? If this is the case, then we would be able to reduce this population balance equation substantially. For example, if there is no spatial variation, then this term here would automatically go to 0. And all your vectors here, for example, your vector of internal coordinate, this is a multi-dimensional one. In this case, you would not have a vector of the internal coordinate, but you have just one element in this vector because of your single or one internal coordinate that you are picking. And this would reduce the dimension of the population balance equation substantially. So then you would have, if you have 1D and no spatial variation, this is the population balance equation that you would arrive at. Okay, but let us just further push this forward, go deeper, and say that in our particular system, we are interested in only a pure breakage system, whereby your particles do not undergo active growth or shrinkage over time. Okay, and if this is the case, then this term would go to 0, and you would arrive at a very simplistic 1D population balance equation. Note that at this point, this population balance equation, even though it's in its one-dimensional internal coordinate form and with no spatial variation, but it is still a very general population balance equation. Why? Because at this point in time, we have not mentioned or say anything about this source of the sink term. This source of the sink term is the term that will tell us, or rather you input your information such as whether your particle or your population of particles are undergoing breakage or aggregation. This is the term that's going to describe this. And for breakage, it has a specific form, and for aggregation, it will have another specific form. And they are all physics inspired in that sense. So let's just go forward with this. This is the simplistic general 1D population balance equation with no growth and no growth, right? 1D, no growth, no spatial variation. And let's just take this forward and put in the breakage part in the source and the sink term, and let's examine how the breakage population balance equation is. Now, this is the general population balance equation in the 1D form, whereby we have no growth and no spatial variation. So if we look at this equation here, this term here is the accumulation term, right? This is the temporal evolution of the number density in the 1D form with respect to time. And then on the right hand side, the source and the sink term, we can write them as two separate terms, where you have a source minus a sink term. The source, we can also call it the birth term, and the sink, we can call it the death term. So the key question that we ask ourselves is, how do we write this for a breakage population balance equation? How do we write the source and the sink term here? So let's just analyze them separately. So first, let's just look at the sink term here first, because the sink term is easy to imagine. Okay, so for the sink or the depth term, what it actually represents is that it represents the breakage of a particle of a size x into smaller pieces. So if you have a particle here and you say that your particle here has a size of x, so the depth term here represents the breakage of this particle into smaller pieces, okay, into particle of smaller pieces. So this is given by the sink term. So the sink term, typically in population balance, we can write it as the breakage frequency, or you can say that it's some sort of like a rate constant. But the difference is that in this case, as you have a range of particles of different sizes, and not every particle of a specific size will break at the same rate, so then we would have this k as a function of x and t. We call it sometimes the rate kernel or the breakage frequency, because just to describe how each size will break, right? Just to describe how each size will break. Okay, so this sink term is the breakage frequency multiplied by the number density function, and the breakage frequency or the rate kernel, this thing here, sometimes we call it the rate kernel, has a dimensions of reciprocal of time. So this is the depth term, which is straightforward. It's just minus a rate multiplied by the number density function. Now let's just look at the birth term or the source term here. Okay, so the source term here, if you consider this particular example here again, when you have a particle of a size of x, now how do you generate this particle here from the breakage of larger particle? Which means that if you have a larger particle here, this particle can break into size of x here. Okay, so for the birth term, we need to sum up all the particles that is larger than x, because all the particles that is larger than the size x has the potential of breaking into the size of x. So this is what the integral means here. We sum up, or we integrate over the entire domain of the internal coordinate from x to infinity. That means all the larger particles, the particles that are larger than x, will break into the size of x. Okay, so that is what is meant by the integral here. And what is within the integral here, this first term here is the average number of particles formed. For example, if you have one particle capable of breaking into two particles, this is what we call a binary breakage. If we have a binary breakage, then this term here is equals to 2. It's just a number. If you have a ternary breakage, your particle is capable of being fragmented into 3 pieces at any one time, then you would have this as 3. Of course, in more complicated case, then your particle would change their behavior. For example, initially it might just break into 2 pieces, and then as time goes on, some underlying physics has changed for the process, then it can break into 3 pieces. Now that is also possible, but for the sake of simplicity, let's just say that this is just a number here. If it's binary, it's 2. If it's ternary, it's 3, and so on. Okay, and then similarly, you also need to characterize the breakage frequency also, because the particle that is of a larger sizes, when they break into x, right, they will have their own rate of breaking into x. So the breakage frequency must be accounted for by this similar term here. This term here is the same as this term here. Okay, it's just that here we have to describe this by y because of the integral here, right? Because we are integrating over dy from x to infinity. And then this p here, this big P here, is the probability density function that describes the breakup of a particle of a state y into x. For example, you have a particle of, let's just say this is y. All right, how it breaks into x? Is it going to be random? Is all sizes of x that is smaller than y equally probable of being formed from the breakage of y, right? So this will give us the probability density function, how your particle break. If your particle doesn't break randomly, it has a particular pattern of breaking, then this will be accounted for by the probability density function. This, this is the number density function, and this whole thing here is integrated over dy from x to infinity. Again, it represents the breakage of the sum of all the breakage of particles that is larger than x breaking into x. So this is being given by the source term. So putting everything back together, so this will be the 1D pure breakage population balance equation that we are looking at. Now notice that now here we drop the dependence of time for this term, this term, this term, and this term. We drop the dependence of time here because these are the terms that represent the behavior of the system, right? This term, if we still remember, this is the term that tells you whether it's a binary breakage or it's a ternary breakage. This is the rate kernel or the breakage frequency. This is the probability density function. And this similarly is the rate kernel or the breakage frequency. So we drop the dependence of time because we make one important assumption here that says that if your particle is of a random scission type, it breaks by random scission, and it's for example, it has a particular rate kernel or breakage frequency, size dependent or size independent breakage frequency, then it will stay the same throughout the entire process that you are interested in, or throughout the entire duration for which you wanted to model the process. So it doesn't change. For example, it doesn't change, let's say, the behavior from a random breakage and then suddenly it becomes an erosion or attrition type of breakage, right? The breakage behavior doesn't change, so it's not time dependent. And it doesn't say suddenly go from a binary breakage to become a ternary breakage. Then all this, you can drop the dependence on time. So the next thing that I'm going to quickly run through is that we should also, after writing the population balance equation, we should also always make sure that the units for each and every individual term in the population balance equation is consistent. is consistent. I can never stress or emphasize this enough. Make sure that when we write an equation, we have to check each and individual term and make sure that their units are consistent. So I'm just going to flash this here and just let you see the units of each individual term here. So we must always make sure that the equation is consistent in terms of the unit. So you can check this and verify this for yourself. Okay, so I'll jump straight to the next important detail that I want to discuss about. Now, I want to talk about one of the most important thing to consider when we talk about solving or implementing population balance modeling, which is the constraint that we must strictly obey when solving this system, right? So this is the population balance equation that we have, and one of the most important thing that we have in this equation here that will define your system is this thing here, which is your probability density function, right? We call this the probability density function, or sometimes in other literature we say that this is what we call the stoichiometric kernel. Right? We sometimes also say that this is what we call the stoichiometric kernel. Okay, so this is the part of the equation that actually tells you how your particulate system is splitting or fragmenting or breaking. What is their probability density function? For example, if you have a polymer chain, right? Let's say you have a polymer chain with 5 monomer. So this is the parent polymer, and you want these things is capable of being breaking into the smaller size polymer, which we call it the daughter polymer. So will the bond break here or here or here or here, right? The probability density function will tell us how the bond breaks. What's the behavior of this bond breaking behavior? For example, is every bond here equally probable of breaking? So if it's equally probable of breaking at each and every bond here, then we call it a random scission process. So this probability density function or the stoichiometric kernel here is instrumental in defining the behavior of the solution of population balance equation. But there are certain rules that we must obey by when we actually model this part in the population balance equation. The first one being that there is something called the normalization condition. Okay, so when you have a probability density function here, or your stoichiometric kernel here, this stoichiometric kernel or probability density function here, when we write it this way, it means that this y here is the parent, okay, particle, and this is the daughter. So this is the probability of a daughter being formed, of a particular size being formed from the parent particle. So when we integrate over this probability density function over dx from 0 to y, okay, it must be equals to 1. So this is what we call the normalization condition. Now the second constraint here has something to do with the conservation of mass. Now this condition here says that the probability density function, okay, of a, when you have a, let's say you have a particle of a parent particle that breaks into a daughter particle, this is your probability density function. And if your daughter particle is larger or equal to the size of your parent particle, then the probability density function is going to be 0. Now this makes sense only, right? Because for a breakage process, you expect your parent particle to break into your daughter particle. So then mathematically, the daughter particle, if it's larger than the size or larger than equal to the size of the parent particle, then you cannot have a probability density function there, right? So it has to be 0. So this is the second condition. The third constraint is also about conservation of mass. It's what it says here is that this term here, this right hand side integral here, should be lesser or equal to the size, or lesser or equal to the size of the parent particle. Okay, so let's just take an example here. Let's say we have binary breakage. So this thing here is 2, and let's say we pick a probability density function of a simple random breakage. Okay, so for random breakage, what we are saying is that this thing here can be given simply as the probability density function can be just simply given as 1 over y. So this is the random breakage probability density function. So this integral here will be what? Integrate from 0 to y. You have x multiplied by, this is 2 multiplied by this, 2 over y and dx. So we expect that this integral here should be less or equal to y. So can we do this? We integrate this with respect to x. This will give 2x squared over 2y. Okay, and this is y and 0. So this is what? This will give us, we can cancel off the 2. You will get y, right? Because the second term is 0. So this inequality holds. Okay, if there is no loss of mass, that means that when your particle is breaking, there is no reaction or something that actually sucks up the mass from the system, and everything is just purely by just breakage, right? There's no reaction that sort of converts the particle into something else, or eating them up. And we know that for such a pure breakage system, the mass should be conserved. Then this integral should be equal to y. But if you have a reaction, let's say your particle is of a chemical species A, it's made up of chemical species A, and during the process is being capable of being converting into something else, then you have a loss of mass, then you have less than y for this integral. Otherwise, it should be equal to y, and this will tell us, or rather it enforces the conservation of mass. So this is the third constraint. Now the last one has got to do with what we call a symmetry condition for the probability density function. Now what this simply means is that if you have, let's say we use the polymer example again, if we have a polymer with a chain length of 5, and let's just say that it breaks into a polymer, a dimer and a trimer, right? Because 5 you can break into 3 plus 2. So what it simply says here for this last condition is that the probability of breaking into this dimer here must be the same as the probability of breaking into this trimer here, right? P of y breaking into x must be equals to P of y breaking into y minus x, because it must enforce the symmetry condition. You cannot have any other thing else. So these are some of the constraints that we must respect when we solve the population balance equation, in this case for breakage. Now let's do a final recap of what we have gone through so far about the 1D population balance equation for pure breakage. So this is the 1D population balance equation for pure breakage with no growth and no spatial variation. This left hand side here is the accumulation term. This term here is the so-called birth or the source term, and this is the death or the sink term. So we can see that the accumulation term is a result of the birth and the death term. Okay, and the population balance equation that we have here, the terms that are highlighted in yellow, this is the rate kernel or the breakage frequency, and this is the terms that are related to how the particle breaks. In a sense, the probability density function, whether it's a binary random or it's ternary something else. Okay, and most of the time we can combine these two terms here, and we can just write it as bxy, right? Let's just say if we know that you are having a binary random breakage, then this b, x and y will be just 2 over y. This is the kernel, the probability density function considering binary breakage for a random breakage system. Okay, so these colored items here, the rate and the probability density function here, are the functions that we call the phenomenological functions, because this gives the behavior of the population of particle undergoing breakage that we are concerned about. And these functions here describe the behavior of a single particle in their local environment. So by definition, this is the definition of the phenomenological function. So what we hope to achieve by population balance modeling is that if we know what are these so-called phenomenological function, the behavior of a single particle in their local environment, then hopefully we can use this to predict the behavior of the population as a whole. Okay, so in doing any modeling or in modeling any particular system, I would say that these functions here are the key things that we seek after. Let's say if we are given a bunch of data and we are trying to model how they evolve by population balance modeling. So these are the primary functions that we are trying to model or extract from the system, because this will give us insights on how the population is behaving, what is the rate that they are breaking, right? Whether it's size dependent, whether it's size independent, whether it's a power law, breakage frequency, and then how they are breaking in terms of whether it's going to be random, it's going to be U-shaped or whatever, right? Whether it's an attrition model, erosion, or we call it chain incision in polymer language. So these are the most important things that we want to model for population balance equation for a breakage system. And last but not least, I want to also bring to your attention that conservation of mass is a very important detail. It is a very important thing in using population balance modeling. In a typical system of population of particle, we typically also say that the first moment of any particle population, right, is given as integrate from 0 to infinity the internal coordinate multiplied by the number density function, right? This is for 1D case, dx. So this is the first moment. So what we typically say is that for a system in which you do not have any reaction that sucks up the system, it doesn't get converted, it's like a pure breakage system, mass must be conserved, then the first moment must be a constant quantity. This is to enforce the conservation of mass in terms of looking at the population balance equation as a whole, right? What it means here is if we take the population balance equation for 1D pure breakage and we integrate with respect to x, we take x multiplied by the number density function, we integrate with respect to x from 0 to infinity, then this term here should be 0 because this first moment here is constant. So this d dt of this first moment has got to be 0. So this is looking at the population balance equation as a whole. Now what I've shown in the previous slide where I list out all the different conditions like normalization, symmetry, and all those are for the user when they are trying to model the system, when they are trying to model the probability density function. They should always make sure that the probability density function that they get from the data, but that they try to model from the data, respect those rules that are being laid out here. And then when we solve the population balance equation, either by numerical methods or by some other moment methods or analytical solution, we must also make sure that the first moment is a constant. Okay, so that is about all for 1D pure breakage population balance equation, and thank you for watching, and I'll see you in the next video.